All right, everyone, welcome back to my channel. My name is Ryan Schul. I am trying to achieve a self-imposed goal of creating 365 machine learning slash data science slash artificial intelligence slash deep learning slash whatever videos in 365 days. I started on August 8th, 2024, and we're about 160 days into this self-imposed goal that I'm trying to achieve, and I've got almost 160 videos at this point. So I'm right on target with where I want to be. In today's lesson, I want to take you through distance metrics and show you how these are used in the machine learning world. Of course, we're using Python and Jupyter Notebooks to do everything. So why do we measure distances, and what are these distances that we're measuring? There's basically four types. There's actually more than four, but we're going to focus on four primary types today: Euclidean distance, Manhattan distance, Minkowski distance, and Hamming distance. Okay, and there's pros and cons to use in each one. Euclidean distance is basically the distance between point A and point B based on a straight line. This is as the crow flies. Okay, so straight linear distance between 2 points, that will be the shortest distance. And this is widely used in k-means clustering, KNN, k-nearest neighbors, PCA, principal component analysis for decomposing high feature data sets into lower features. So I've got a couple videos on that. You can check it out. Manhattan distance, it's a little bit different. You follow longitude and latitude coordinates, but they have to be akin to the distance that taxi would drive along city streets in Manhattan, right? So that's why it's called Manhattan distance. And we look at horizontal and vertical movements. So no straight lines like Euclidean distance. These are horizontal and vertical movements only. Minkowski distance is measuring distance between two Euclidean and Manhattan distances. So it's kind of a combination of Euclidean distance metric and the Manhattan distance metric. Why do we use it? It's flexible and allows us to change the behavior of a distance metric, right? So it's kind of using the best of both worlds, right, without the constraints of either one, okay? And again, this can be used in KNN types of analysis or clustering algorithms. The last example we'll see today is Hamming distance. This is basically looking at the number of positions between two strings or two binary vectors of equal length. So it's very different from the first three, right? In the first three, you're measuring like distance between A and B. With a Hamming distance, we're actually looking at comparisons of two strings and how similar or dissimilar they are. A little bit like cosine similarity. We'll see just a quick view of that. Not really in this demo, I'll just show you a picture in a minute what that looks like. And I do have some videos on cosine similarity, so you can check that out if you want to learn more about that. So this is really binary categorical type of data analytic that could be applied for a couple different purposes, basically string matches. And again, this is used for a text or a sequence analysis. Let me skip to the end because I think a visual will be useful here, and we can see it over here. So Euclidean distance is as the crow flies, straight distance, shortest distance. Cosine similarity, I'm not going to cover today. I have another video on that. Hamming distance, this is the fourth of the four that I just mentioned. Manhattan distance shows latitude, longitude coordinates, right, in a straight vertical or horizontal line. Minkowski distance, we're going to look at that, right? It's kind of a combination of Euclidean and Manhattan. And there's a few other distance metrics. Chebyshev, Jacquard is pretty popular. This is typically used for measuring similarities in names between names in columns of an Excel file or names in columns of a database. Sorensen dice is another metric. We're not going to touch on that. Haversine is one more way to measure distances based on longitude, latitude coordinates in a geosphere kind of environment like our Earth, like the world, okay? And I have a couple of videos on that. You can check that out. So today we're going to focus on these four: Euclidean distance, Manhattan, Minkowski, and Hamming distance. So I'm going to go ahead and import the canonical, very typical, one of my favorite data sets. This is the empty cars. You can see miles per gallon, cylinders, so on and so forth, gear ratio, and carburetors for all the cars. We're visualizing that. I'm going to take the differences between the distances based on these four metrics in this data set. So if I hit Control Enter, we can see these are the four metrics: Euclidean, Manhattan, Minkowski, and Hamming, right? And we're looking at the KNN R-squared score of each. So closer to 1.0 is better. 0.99, 0.98 is going to be a very close approximation for the goodness of fit between the data points. That's what R-squares measures. right? Anything 0.9 and above is still good fit. Definitely not perfect, but we're doing good. 0.89 is pretty decent. 0.87 is good, and 0.83 is okay. Anything over 0.7 0.70 is considered statistically significant, but again, the higher the better. So if we achieve 0.8, 0.9 r squared, that's going to be a better fit, right? So Hamming distance is okay. It's really looking at similarities between different strings. And if you look closely, these are all metrics. There's no strings here, so that's why this one is performing lower, and the Euclidean distance is going to be the most efficient. And again, we get the actually, like the vertical horizontal distance, Manhattan performs best. 0.89 is the highest r squared. Euclidean is close. This is taking the best of both worlds, but it can't quite achieve the r squared that Manhattan and Euclidean distance are giving to us. Okay, so here we're measuring the actual distances. When you refresh this, we're looking at distance metric, and we're using the number of clusters here. K-means cluster. We're looking at 3 different clusters to look at how closely these distances are, or how similar they are, or how dissimilar they are. So you can see Euclidean distance, 1 point, 1 point, 2.6. Those are pretty lower. Distance Manhattan, 3 point, 3 point, 2.9, 0.6 point. So not quite as tight, crisp as the Euclidean. And Minkowski is 1.2, 1.0, 0.8. So pretty close there. And the distance Hamming is 0.8, 0.8, 1.0. Okay. So Euclidean distance, we're looking at the straight line as the crow flies, right? That's what we mentioned before. Manhattan distance is looking at the way a taxicab would drive on city blocks, so vertical and horizontal movements. Minkowski shows the combination of the Euclidean and Manhattan distances blended together, and Hamming really looks at differences in text, how similar text is or how dissimilar text is, kind of similar to what you would see with cosine similarity, right? So let's go ahead and plot the differences in a bar plot here. So we have bar plot, and we're looking at different distances. So Euclidean average distance is 1.7. Manhattan is 4.17, so not quite as efficient. Minkowski is taking the best of both, so the average distance is actually pretty good, and the Hamming distance actually performs the best. The average distance between all the different metrics over here is 0.9. Okay, so that's kind of interesting. I didn't think that would outperform the others, but it actually does. All right, so if you're looking for the most efficient way to calculate distances, you really have to look at all 4. I thought the Euclidean or Minkowski would be the best. Usually that's the way it is. In this case, Hamming outperforms those 2, and Manhattan is really usually not the best, because you're subject to those constraints, only vertical or horizontal, right? Where Euclidean is going straight. Usually the straightest distance is the closest distance, but in this case, Minkowski outperforms that. And this one, Hamming actually outperforms both. Okay, so let's look at a slightly different view here. This chart is called a box plot, and it shows you the averages as well as the outliers here. So the first quartile is 1.31. The minimum is 0.727. So if you go down here, 0.727 at the bottom, right here, median is 1.67, and the max is 3.59. So you can tell that this is going to be pretty tight. You can tell that this Manhattan distance is kind of more dispersed, because you look at this, and this bar is much taller, this bar is shorter, right? Minkowski is even shorter. So you look here, the median is 3.7, the max is 8.73, maximum distance 8.73, minimum is 1.21. Minkowski is actually the best performing distance metric calculation here. 1.32 is the median, 0.68 is the minimum, and 2.8 is the max. And the Hamming is the best of everything here. 0.8, I think it's 0.8 for the minimum, max is 1, and the what's the median? 0.9. Okay, so this chart right here pretty much matches what we would see over here, but showing the outliers as well, right? Let's look at one more example over here. It's a scatter plot. Okay, scatter plot using Plotly. I like these Plotly charts. I use these a lot. You can tell the higher Euclidean distance right here is, let's see, horsepower and miles per gallon. So the horsepower is 335 for this car. Miles per gallon is 15. You'll see this all the time in this data set. The higher the horsepower, the lower the miles per hour. miles per gallon. Sorry, miles per gallon, because it's a sports car, right? That's all this. This is 215 horsepower, 10 miles per gallon, and this is 205 horsepower, 10 miles per gallon. So that actually, the sports car is a little bit better. You get about 100 and over 110, 120 more horsepower, and actually better miles per gallon. So this is evidenced by the Euclidean distance. This car might be something that we might be interested in, right? More miles per gallon and more horsepower. Down here, we get less horsepower, but a lot more miles per gallon. So 33.9, almost 34 miles per gallon at 65 horsepower. So certainly not a sports car, but for the economically minded person, that might be a car that you're interested in. Okay, let's look at another clustering experiment right here. And again, scatter plot. I like these plotly scatter plots. It shows you everything relative to everything else. So you see the different clusters. Cluster 2 is in yellow. Cluster 1 is in magenta or purple or pink, whatever you want to call this thing over here. And then cluster 0 is sort of a navy blue, and we see all the sepal length and the sepal width, the distance to the centroid from each data point, and then the cluster that it falls into too. Okay. So again, we'll look at one more chart, and this is all iris data, right? You can see this data from the iris data set. If I do display the F, do that, print, separate this. I like this way to print characters and do a separation. If you're doing a couple different things in the same cell here, in the same Jupyter Notebook cell, Control Enter to run it, we will display our data frame right there, and these are the characters I just put in just to separate the visual data frame from the clustering. Now the clustering is done slightly different, right? We're looking at the Euclidean distance, Manhattan distance, Minkowski distance, and Hamming distance all together, right? And we're still doing some clustering. So in the yellow, you see the cluster number. This is cluster 2 in yellow. Cluster 1, which is kind of a pink magenta color. Cluster 0 is navy, right? And you can see how these clusters are pretty tight together, right? And the clustering this time is done based on, where is the cluster? K-means centers. The scaled data, and then the centroids, right? So this cluster might be a little bit more intuitive, right? You see all the purples and pinks together, all the navy blues are together, and the yellows are together because these are clustered relative to the clustering now is done on, let's see, clustering and number of clusters. Oh, the scaled data. And the scaled data is everything in the data frame. So everything except for miles per gallon. Now in this data frame, we're taking, again, everything except for miles per gallon and scaling the data, right? So we're fitting and scaling the data X scaled and then feeding that into the k-means clustering algorithm, right? And producing this view down here. So that is pretty much it. So different ways of calculating distance between point A and point B. Euclidean is straight. Cosine looks at similarities of text. So we're not looking at cosine similarity in this video. I have another video devoted specifically to that. That's its own topic. Hamming is looking at the similarities or differences between hex strings. Manhattan is vertical and horizontal distances. Minkowski is Euclidean plus Manhattan combined. Chebyshev is another way to measure distances. We're not looking at that here. Source and Dice, Haversine, and Jacquard are different ways to measure distances or similarities or differences between two data sets, or point A and point B, or longitude coordinates. You would use Haversine if that is the type of data that you're working with. So that's it. I'm going to wrap it up here, guys. Hopefully that was useful and insightful. I will share all this code with you when I post a video later today. Okay, I'm going to wrap it up here. Keep it pretty short, tight, crisp. That's my goal for this one today. Okay, thanks for your time and enjoy the rest of your day. Goodbye.